Hello and welcome to the webinar on how to train a policy for controlling a machine using simulation and deep reinforcement learning. My name is Arash Mahdavi and I'll be your host today. Before we start, let's go through some housekeeping items. First of all, you probably see two screens on right now. One is the webcam that you see me on, and the second one is my screen, the slide that I'm showing right now. When I start the webinar, because it's pre-recorded, I will close the webcam so you can only focus on the webinar itself. And you can click on this icon to go to the full screen view and see the entire webinar at its full view. One other thing that you should pay attention to is this panel that you have access to, and you can configure your audio output here. Our recommendation is to use your own computer audio. If you use the phone call, there might be a little bit of lag between the video and audio. And also you have access to this section, the question section, and you can ask your questions. And we are going to answer some of your questions during the webinar, some of them at the end, the Q&A section. And we also answer all the questions that are not answered during the webinar at the end in the follow-up material. Okay, some important points to note. For efficiency purposes, I've pre-recorded the model building process. I recommend to watch the entire webinar and not worry about following along. You will receive all the material that is related to this webinar, including the model, the exported model, all the code explanations and RL4J library that you need to replicate this webinar. The webinar focus is not on teaching reinforcement learning, and it's mostly focused on how you can use AnyLogic for and build a model, a simulation model for training environment, and also for testing your AI solutions. Majority of the code you will see is copy pasted due to the time limitations. Since the code may be hard to read and follow on a screen right now during the webinar, just focus on the overall description of the code. We will provide the source code and very detailed explanation of what is happening there in the follow-up material. Also, as I mentioned, submit your questions in the question sections of the GoToWebinar panel. And as I said, we answer some of those questions during the webinar. I come back at the end for the Q&A session, and I answer some of the questions that you have. And if there were any that we couldn't cover during the webinar, we'll answer them in the follow-up material. Your feedback is extremely important for us. After the webinar, please fill the survey material that we will send to you in the follow-up email, and your thoughts and suggestions are extremely important for our future webinars and how we can improve these webinars based on what you need to know. Okay, so let's go briefly over the webinar agenda. At the beginning, I go through a brief introduction to simulation modeling and AnyLogic software itself, for some of you who may not be familiar with simulation modeling or the AnyLogic software. Then I move into an introduction to Statecharts, which is like a mini training about Statecharts and introduction to these concepts and how it could be used to build behaviors for different types of objects. Then I move to model definition and overview of what we want to model. The model is about an AGV that we want to control with a policy later on with deep reinforcement learning. Then I show you a step-by-step instruction of how to build that state chart representing the behavior of that AGV, and we are going to use this model as a training environment in the next step. Then we export that model and as a standalone application, and we put it inside IntelliJ, another IDE, and we do all of our training there. We use our L4J library to train our policy, and after we have a trained policy, we put back that trained policy into the AnyLogic simulation model to test its performance and the behavior of the learned policy. And at the end, as I mentioned, I come back for the Q&A section and answer some of your questions. So let's start the webinar, and I'll come back for the Q&A section. Modeling is one of the ways to solve problems that appear in the real world. In many cases, we cannot afford finding the right solutions by experimenting with the real objects. Building, destroying, making changes may be too expensive, dangerous, or just impossible. If this is so, we leave the real world and go up to the world of models. We build a model of a real system, which is its representation in a modeling language. Having built the model, or sometimes even while building the model, we start to explore and understand the structure and behavior of the original system, test how the system will behave under various conditions, play and compare different scenarios, and sometimes we even optimize it. When we find the solution we are looking for, we map that solution back to the real world. The whole modeling thing is actually about finding the way from the problem to its solution through a risk-free world where we are allowed to make mistakes, undo things, go back in time, and start all over again. Simulation modeling is a discipline that tries to explain how something works by building a replica of it. Compared to other types of models, simulation models are extremely versatile. We can say a simulation model is a set of rules that defines the workings of the system being simulated. A simulation software such as AnyLogic allows us to set the model's starting state and use the rules we select to simulate the system's evolution through time. In simulation modeling, a method is a general framework for mapping a real-world system to its model. You might think of it as a language that allows you to communicate the simulant's inner workings with the simulator. Of course, simulation methods weren't all created at the same time. They also weren't created with the same type of simulant in mind. That's why each simulation method works better for a specific scenario. In discrete event modeling, the modeler considers the system being modeled as a process. In other words, a sequence of operations being performed across entities. System dynamics is a method of studying dynamic systems. It suggests that you should take an endogenous point of view and model the system as a causally closed structure that itself defines its behavior. Feedback loops or circular causality in the system are the heart of system dynamics. You may not know how the system as a whole behaves, but you may have some insight into how the objects in the system behave individually. In agent-based modeling, you can start building the model from the bottom up by identifying those objects or agents and defining their behaviors. Sometimes you can connect the agents to each other and let them interact. Other times you can put them in an environment which may have its own dynamics. Global behavior of the system then emerges out of many concurrent individual behaviors. Multi-method modeling is a mix of the three modeling paradigms. There is a significant synergy between different simulation methods, and this means the capabilities of multi-method models are greater than the sum of their parts. AnyLogic software is the champion of the multi-method modeling approach and the only platform that allows you to build truly unrestricted multi-method models. There are many architectures, mixes of simulation methods possible for multi-method modeling. AnyLogic is the market and technology leader in business simulation. It supports all three modeling methods and any kind of multi-method modeling. It supports multiple visual languages such as process flowcharts, stock and flow diagrams, state charts, and action charts. It also integrates with GIS maps, has built-in databases, and it has vertical libraries. With the help of material handling library, you can simulate and analyze end-to-end processes on the factory floor as well as in storage facilities. With the library's functionality, you can evaluate site and factory layout alternatives to implement them and increase shop floor performance. You can also analyze production line design and performance and test its capacity for production ramp-up. You can allocate factory resources, including staff and equipment, to avoid unforeseen bottlenecks and provide simulation-based scheduling. You can also manage AGV fleets and simulate their interaction with conveyors, manufacturing machines, and operators. You can also simulate warehouse processes, including conveyor and AGV routing. The pedestrian library is useful when simulating pedestrian dynamics in urban landscapes, open events, museums, shopping centers, and transport hubs. At a preliminary project design stage, pedestrian simulation models will help assess the ability of a facility to cope with the planned loading and comply with safety requirements. At an operating facility, the pedestrian library capabilities will be instrumental when evaluating capacity, mobility, and accessibility issues. During reconstruction, the crowd management tool will support testing the plan changes and determining the best solution. AnyLogic Rail Library allows you to efficiently model, simulate, and visualize operation of rail yards and rail transportation of any complexity and scale. Classification yards, rail yards of large plants, railway stations, rail car repair facilities, subways, airport shuttle trains, rail in container terminals, or even rail transportation in a coal mine can be easily modeled with this library. The Road Traffic Library allows you to model, simulate, and visualize vehicle traffic. The library supports detailed yet highly efficient physical level modeling of vehicle movement. It is suitable for modeling highway traffic, street traffic, on-site transportation at manufacturing sites, parking lots, or any other systems with vehicles, roads, and lanes. The Fluid Library allows you to model storage and transfer of fluids, bulk matter, or large amounts of discrete items, which you do not want to model as separate objects. The Fluid Library interoperates with the Process Modeling Library. It can convert agents into portions of fluid and vice versa. AnyLogic Cloud is a secure web platform for running simulation models. With AnyLogic Cloud, you can share models with your customers in a ready-to-use cloud environment, no software rollout needed. You can store, organize, and edit experiments and scenario data, including model versions, run parameters, and simulation results. You can leverage a range of experiments, including parameter variation and Monte Carlo. The cloud scenario comparison option helps visualize results from different experiments to better highlight key metrics. You can perform complex multi-run experiments faster and more efficiently than on a regular computer. Being scalable by design, AnyLogic Cloud can rapidly respond to meet computing demands and execute experiments on multiple nodes and cores. The cloud platform, you will find advanced charts and graphs like box plot, scatter plot, or surface plot. You can create dashboards using intuitive drag and drop style and configure them to suit your end users. To download AnyLogic, please go to anylogic.com and click on the download button. The entire example shown in this webinar could be replicated in AnyLogic PLE, which is free. The only restriction would be exporting the model as a standalone application, which needs a full AnyLogic professional license. Because of that, we'll provide the exported model with the webinar supplemental materials. You can download AnyLogic for Windows, Mac, or Linux operating systems. If you want to start learning AnyLogic, one great option is to go to the Resources tab, where you will find several books and other educational material. For example, majority of definitions in this webinar are taken from the Big Book of Simulation Modeling. If you want to learn more about AnyLogic's capabilities and its application in your specific industry, go to the Purchase tab and contact the sales team in your region. A state chart is an extended version of a state diagram and is a visual construct that enables you to define event and time-driven behavior of various objects. State charts are used a lot in agent-based models and also work well with process and system dynamic models. State charts consist of states and transitions. A state can be considered as a concentrated history of the object and also as a set of reactions to external events that determine the object's future. The reactions in a particular state are defined by transitions exiting that state. Each transition has a trigger, such as a message arrival, a condition, or a timeout. When a transition is taken or fired, the state may change and a new set of reactions may become active. As an example, let's take a look at a state chart that represents the behavior of a watch. This watch is capable of showing date and time We can also set an alarm on this watch, and also based on its current level of power, it might go into a suspended state. To toggle between different functionalities of this watch, we have access to a button called A, and by pressing it, we can toggle between showing date, time, and alarm. In the state chart, we can clearly see that this watch has 4 simple states: showing date, showing time, setting alarm, and suspended. We can also see that showing date, time, and setting alarm are inside a composite state called normal. This is done because we wanted to bundle them into one encompassing state. There are 7 transitions that can trigger a state change. At any point in time, only the transitions that are connected to the current state are active. For example, here, showing date is the current state, and because of that, the blue and red transitions are active. We are also in the normal state, and because of that, the green transition is active too. There are different trigger types for transitions. For example, these blue transitions are triggered by a message. These 2 red transitions are triggered by a timeout. And these green transitions are triggered by a condition. One important rule about the state charts is that you could only be in a single simple state at a time, and because of that, there shouldn't be any ambiguity about where you are in a state chart at any point in time. For example, at the initialization, we should know exactly in which simple states we are, and because of that, each state chart needs to have a state chart entry point. In most cases, namely each time there is a transition or a pointer pointing to the composite state, you need to identify the default initial state inside the composite state. This is done by the initial state pointer. Okay, let's take a look at the actual state chart during the runtime. As you can see, we have a power level that starts with 1, and every second we are depleting that power level by 1/100th of a unit. The state chart enters the normal state, and showing time is the simple state inside this composite state. If I press A, this message transition is triggered and we are going to showing date, and after 5 seconds we go back to showing time. If I press A again, I go back to showing date, and if I press A again before that 5-second timeout, I go to setting alarm. Now I have 5 seconds to press A again to going back to showing time, or the timeout will take me there. If I press A 3 times, it takes me to showing time. As you can see, the power level is about to hit the threshold that takes me to the suspended state. And if I want to go back to the normal state, I need to recharge, set the power to 1, and then it goes back to the normal, and it goes to the showing time because it's the initial state inside the composite state. The simulation model is about an automated guided vehicle, or an AGV. This AGV moves forward and its final destination is the circle. It also carries a battery that supplies its power, and the level of the power is shown with this rectangle. To represent its state, we are building a state chart, and that state chart has an operating state, which is a composite state, and inside that we have 4 simple states representing each of these areas, and the win state at the end represents the final destination. To recharge its battery, the AGV can toggle between the recharging and operating state. Whenever it toggles back from recharging, it has to start from state 1, and if the battery is fully depleted, it gets to a dead state. Moving forward in the state chart is based on messages that we pass to the transitions, and we can move forward from state 1 to 2, 3 to 4. So if I press forward once, see a message is passed and the AGV moves forward. If I press the backward, a message is sent and we move back from state 2 to 1. If I say backward in state 1, it goes back to itself, which is state 1 again. Moving forward, another forward, takes us to state 3. Here we have to wait for 5 seconds before the swirl goes down and lets us to get to state 4. If I go back to state 3 and try to push forward
before that 5 seconds, it actually takes me back. So the idea here is in state 3, you have to wait for 5 seconds. Otherwise, if you try to move forward, it actually takes you one step backward. And at this point, you can see that our battery is pretty low. And if I keep struggling here, it goes to a dead state because our battery is fully depleted. We have to be careful about that, and before that happens, we have to start recharging the battery. Let's try some scenarios. To get to the win state, I have to move forward in state 1 and 2. Then I need to wait for 5 seconds, state 3, and then move forward in state 4 again. Each forward movement depletes the battery by 10 points, and each wait by 2 points. Therefore, in ideal case, we expect the ratio of the power to the power capacity to be 60% or 0.6. In this scenario, we added a slip chance to each forward movement. For example, here I try to move forward, but I slip back to state 1. If I press forward again, this time I was successfully moving forward. I'm waiting for 5 seconds. And because of that extra step, the power level is going to be 10 points lower than the ideal case, and our score is going to be 50%. Knowing that there is a slip chance, the best strategy is to recharge your battery whenever you slip back to state 1. Basically, you start fresh with a full battery and test your luck again. As I demonstrate here, I slip to state 1. Now it's better to recharge the battery and then start over again. I slipped again, recharge the battery, start again. We slipped again, so I need to toggle to the charging state, fully charged, and try again. Okay, wait for 5 seconds, getting to state 4, try forward, we won, and you can see we have the ideal score of 60%. Okay, click on the new model icon. Our model name should be RL Statechart, or the name you select. And the model time unit will be the default, which is in seconds. Next step is to go to the Statechart palette and drag and drop the Statechart entry point. And we're adding 2 of our main states. The first one is going to be the operating state, which is this one, and I'm adding the second one, which is recharging state. So we can click here and rename them to operating and recharging. Next is to add the transitions between these 2 states. And when you have a hanging transition, it will be in red, so you have to make sure they're correctly connected. You can adjust those icons. Both of them should be triggered by messages. Operating state is a composite state, and we have 4 simple states inside it. I'm starting with state 1, and by copy pasting it, I make the next 3. We have a final state at the end here. We can adjust them, and now I'm going to add some branches between these, some of these states. I'm going to add transitions to and out of these branches now. And all of these transitions are going to be triggered by a message. So we have to click on them and adjust that. We do the same for the second branch, a message. The transition between state 3 and 4 is going to be a timeout. This is different from the others. It's a timeout, and the timeout time is going to be 5 seconds. Again, another message transition, and the last one to the final state. The transitions that we modeled so far are for the forward movement. Now we are going to add transitions that represents the backward movement. And for state 1, because we don't have any prior state, it will be going back to itself, but for the rest, we'll go back 1 state. Here, state 2 to 1. The backward movement for the next one would be from state 3 to 2. We can do some adjustments here. And if you zoom in, you have access to more refined grid lines. And I'm adding the backward movement from state 4 to 3. All of these transitions are going to be based on messages. One exception about the forward movement is when you're in state 3 and you try to move forward and it actually goes backward, and that's what I just did. Now I'm going to rename this final state to wind state, and I'm showing its name. So we need some transitions that represents when this machine sleeps and returns back to state 1, and those happens at these branches, and because of that I'm adding 3 transitions back to state 1, and these are going to be based on a condition that brings us back to state 1. So I add all 3 and I make some adjustments to make sure everything is aligned. And as I said, by zooming in you can have access to a more refined grid line and make more refined adjustments. Now I'm adding the second final state. This is going to be the dead state, and it's connected to the operating composite state. And it's based on a condition, and we will set the condition later. We are also going to have an internal transition inside the recharging state, and that is going to be active as long as you are in the recharging state. And it's going to be a timeout with timeout of 1 second. We can change the color of these states, for example, to show them in a more clear way. When we enter a composite state, we need an initial state pointer that tells us which is the initial state when you enter that composite state, and in our case it's going to be a state 1. Now it's time to add all the parameters and variables that we need in the model. I go to the agent palette and I add a parameter here by dragging and dropping the parameter icon. I rename it to use policy, and it's going to be a Boolean, and we are setting its initial default value to false for now because we don't have a policy yet. The second parameter is going to be a sleep chance. This is the percentage of sleep chance going back from any branch back to state 1. And the default value for now is 20%. In the training, I'm changing it to 30. Now we need 2 variables to set the values for each movement, the cost associated with movements. The first one is an action cost, which has a value of 10. I copy pasted that, and I'm going to rename this to the weight cost, and that's going to cost us 2 points or 2 units of battery. And now I'm adding variables related to the battery. So it's going to have a power capacity and also the power level. So the first one is a power capacity, which has the initial value of 100. It's going to be a constant because it's not going to change at all during the simulation. The second one is the current level of battery power, and the initial value of that is going to be power capacity. Now it's time to set the values for the messages that are triggering these message transitions. And for the forward movements, the message should be 0. So I'm clicking on all the transitions that represents the forward movement, and I change the message value to 0. This one is timeout. We are not changing that. So this is also a forward movement. And if you remember, we have this exception going back from state 3 to 2. That's also a forward movement, and the value for the message should be 0. For the backward movement, the value for the message that triggers that backward movement is going to be 1, and I'm clicking on all of them one by one and change the message value to 1. So we have 4 of these. Next is to set the message that triggers the toggling between the operating and recharging state, and the message value here is going to be 3, both for toggling from operating to recharging and back from recharging to operating states. Now we need to set the action that happens as long as we are in the recharging state. And I click on it, and what is happening here is we are keep adding 25 points to the current level of our power or battery. To make sure that the power level does not go above the maximum capacity, we are using this limit max function, and we add 25 the current level of the power, and the maximum would be the power capacity. That's the code that we associate or assign to the power level as long as we are inside this recharging state. Next is to set the condition for transition to the dead state. And the condition for that is going to be when our power level is less than or equal to 0 if we do not have any battery charge, and it goes to the dead state. As you remember, when we are reaching a branch, there is a chance that we slip back to state 1, and we are going to set the condition for that slippage. And the condition is a random true distribution based on our slip chance. And for now, it's going to be 20%. So 20% of the time when we reach to that branch, we might slip back to state 1. And we basically, I'm copying, pasting the code to all those 3 transitions. Now it's time to add the functions that we need for our reinforcement learning training. And the first one that we are adding here is get observation. This is the function that communicates the current state of the system to the learning agent. And as you can see, it's a function that returns an array of doubles. And the first thing that we do is we are going to get all the states that belongs to the state charts and add them to a variable called states, and that's an array of all the states that belongs to the state chart. Okay, so now I'm going to declare a new variable, and it's an array of doubles. It has 12 elements. The first 11 elements represents which state of the state chart we are in right now, and the 12th element tells us the power ratio. And this is the value that we are returning at the end in the return part of this function. We want to represent the observation with a one-hot array. We're going to loop through all the states that we found and add value 1 to the observation if we are in that specific state, and the rest of the states will be represented with 0. Okay, so that's the loop. Here, we get that specific state from the array that has all of our states. And in our observation array, we set a condition. If you are in that state, the value should be 1. Otherwise, it should be 0, which builds us that one-hot array that we wanted. The 12th element of this observation array is the ratio between the current level of the battery power and its maximum capacity. And this is what we are doing here. We find the last element and we assign that ratio, the current level of the power divided by the power capacity, to that 12th element. And at the end of this function, we are returning this observation array. To make sure that your code compiles okay, you can click on this build button and check it. The next function is take action. And it has an input or argument that is called action, and it's an integer. And by passing this argument, we tell this function what to do. If you look at the condition, it says if this passed argument, this action variable, is equal to 0, or if it is equal to 1, you have to reduce the power level, the current value of the power level, by the value that we set in the action cost variable, which is 10 units. Else, if the action that we want to take is equal to 2, which is waiting, the power level should be decreased by the wait cost, which is 2 units. Besides depleting the power level, the action function also sends this action to the state chart. And for doing that, we are calling the fire event method of the state chart, and we pass the action to that. So it could be anything between 0 to 3. And the last function that we are adding here is calc reward, and it calculates the reward that we want to return. And the value is a double. And the value that we calculate here is based on the current state of the state chart. We are using a method called inState to check the current state of the state chart. For example, here, the first if statement, we are checking if we are in the win state, and if we are there, we are returning the ratio between the current level of the power and the power capacity. So for example, if our power level is at 60, the value would be 0.6. Next condition would be if we are in the dead state, and if we are there, the reward that we are going to return is going to be -1. And in all the other cases, we return 0. So that is our reward scheme. And it only gets a reward if you are in the win state or dead state. So there is no intermediate reward. We also need to select all 3 functions and set their access to be public. This is needed for our experiment, which happens inside IntelliJ outside of AnyLogic. We do not need to be able to control the state chart manually for the reinforcement learning to take place, but to be able to experiment with the model and better understand its behavior, we're going to add 4 buttons for manual control. Add a button from the control palette and name its label forward. In its action field, we call the take action function and pass value 0. As we defined before, action 0 means sending a message to the state chart that triggers forward movement. We will also add a text object from the presentation palette and put it above the button to show that if pressed, this button sends a 0 message to the state chart. We now make 3 copies of the button and its text object and change their label to backward, wait, and toggle. The value that is passed in their action field are 1, 2, and 3 respectively. Here we add an output object from the analysis palette and rename it to score. We call the calc reward function on simulation end to show the final reward received at the very end. To finish and stop the simulation when we reach a final state, we call finish simulation function in the action field of win and dead states. We do this because there is no reason to continue the simulation after reaching a final state. Finally, to visually represent the current level of power in the battery, we will add a rectangle from the presentation palette and change its fill color to yellow-green. We need to rotate the rectangle 180 degrees to show the level correctly. Now we click on the equal sign next to the fill color field to change it to dynamically evaluating and type this ternary operator. This operator says that if the current power level is more than an action cost, which is 10, show yellow-green. Otherwise, show red. This serves as a visual cue to us that the power level is low. The height field also should be changed to dynamically evaluated. Here we need to multiply the original height of the rectangle 230 in this example by the ratio of the current power level to the power capacity. Because the rectangle height will dynamically change, we will add a second rectangle to show the border of the battery level by having a line color but no fill color. Before we can run the simulation to manually control the state chart, we need to make some small changes to the simulation experiment's properties. We can change the slip chance here and experiment with different values. In the training, we will use 0.3 to encounter more slippage, but here we will only set it to 0.2. Make sure that the random seed is selected so that the simulation runs will be unique. Now we can run the simulation and start controlling the state chart manually. If I press forward, we're supposed to move forward, but as you see, it slipped back to state underline 1 and we lost 10 units of charge. My second attempt was successful and it moved to a state underline 2. If I press backward, it definitely moves to the previous state. I now keep pressing forward to reach at state underline 3, where I must wait for 5 seconds before the timeout transition is triggered. After that, I pressed forward again and it successfully moved to the win state. You may have noticed I did not press the wait button 5 times when I was in state underline 3, and because of that, the power is not depleted by 5 times the wait cost, or 10 points. If I had, the correct score would have been 0.1 instead of 0.2. Although it is not necessary and has no effect on our reinforcement learning training, in the next steps, playing with these manual buttons to control the state chart will give a very good insight into what the AI is going to observe in its interactions with the model. The conventional way of extracting information and decisions from a simulation model is through experiments. For example, AnyLogic lets you to do parameter variation, Monte Carlo, compare runs, sensitivity, optimization, and custom experiments. In all of these experiments, a decision maker is interacting with the model and explores the spectrum of possibilities to improve their decisions. In reinforcement learning, we substitute the human decision maker and let the AI experiment with the simulation model to learn a policy. This learned policy is capable of making optimal or near optimal decisions over time. To make this happen, we connect the simulation model that we just finished building with a learning agent. The learning agent controls the AGV and tries different actions and discovers the ones that yield the most reward. For the training environment, we are going to use IntelliJ, and if you don't have IntelliJ, you can download it from JetBrains website, as I'm showing it here, and it has a community version that is free. You go to the download section and download this community version. Before exporting our model, we need to make a custom experiment. You can right-click on your model name, then select New Experiment, and here I'm selecting a custom experiment. You need to have an AnyLogic professional license to be able to do that. And when you're making a custom experiment, it it generates some default code here. We don't need this. Select and delete this code, and now we are ready to export our experiment. Right click on your model name, export, and you have two options. We are selecting to a standalone application. We need to save the model, and here in the destination folder, you can set it up to be the place you like on your hard drive, and then the experiment to export, we are selecting this empty custom experiment that we just built. Press finish, and the model is now exported. So in the opened exported folder, you can see the model jar file. There is this lib directory that you can see AnyLogic engine files, and inside this query DSL you see database related jar files. These files are needed for running the model from inside IntelliJ. Now from IntelliJ we are building a new Java project, and the project name, I name it AnyLogic Webinar. You can name it as you wish. And now I'm inside this newly built project. Here you can expand these sections, and if you go to the project structure, you can see the SDK that we are using. It should be something 9 or higher. Now we are ready to add our external libraries. Here I go to the exported model folder, and we are adding the necessary jar files. The model jar file is the first one. Then I go inside the lib folder and I add the engine files or jar files. And now we need to add the database related jar files. There are 4 of them. We add these. Okay, so we have all the jar files that are related to the model itself. Now I'm adding the RL4J library, so it's part of the supplemental material that comes with this webinar, so you can import that as well. And I click apply, so everything is now added to this project. If you expand this folder, you see all the added jar files to this project. Now right click on the source folder, new package, and I call this package DRL. And I'm going to add a Java class by right clicking on it and add a Java class to this package. I call it training. And now we have our class to write our code in. Here you can see the class name and the package that it belongs to, DRL. Now we are going to copy paste some code here. The first part is the imports. You see the imports that are related to the model itself. The first is the AnyLogic engine. That is here. And the second is RL_Statechart, which is the name of the model or the package that this model has. If I go back to AnyLogic and if you look into the properties of the model under the advanced section, you see the same package name. Going back to IntelliJ, we have 2 Java related imports, and the rest are RL4J related imports and all the classes that we need for that library to work properly in our class code. So now that we are done with the imports, I'm gonna paste the code that is related to the training here inside the training class. I'm gonna briefly explain what is happening here. For a more detailed explanation of this code, please refer to the supplemental material that comes with this webinar. So here the first thing that we did was to instantiate a custom experiment. This is the custom experiment that we added to the model, and you can see it in this project structure. First, to implement this Markov decision process interface, inside it we are declaring an engine variable that is based on the experiment and the root, which is the main in our model. Here it is the observation space, which is an array with 12 elements. We have a discrete space with 4 possibilities for our 4 actions. In the MDP interface, we need to implement several methods, and one of them is get observation. As you can see, we are referring to the get observation function inside root or main of our model. Going back to IntelliJ, the next method to implement is the reset. If we have a running engine, we need to stop it here first. Then we set the seed of this default random number generator to be a random number. We also set the stop time of the model to be 10,000 seconds, a slip chance to be 30%, and action cost to 10 and wait cost to 2. Next is the step method, and here we're taking an action. This is take action function inside your model. Then we run the model for 1 second, and then we get the reward. IsDone method checks if the state chart is in win or dead state and returns true if it's there. Here are some of Q-learning hyperparameters. Here is the maximum number of steps in each simulation run. Here is the maximum number of steps for the entire training experiment. And here is the maximum size of experience replay. Mean epsilon sets the minimum chance of random action. And here is the number of steps to reach the minimum epsilon. This is the setting for our network. We have 2 hidden layers with 300 nodes each. To define the training, we pass the MDP, the network, and the Q-learning configuration. Then we start the training, and we record the output policy in the Statechart online policy.zip file. You can run the training by right-clicking on the training class and selecting Run Training Main. I'm showing the training process with 10x speed. It should take between 10 to 20 minutes to complete. As mentioned, maximum number of steps is set to 100,000 and each simulation run is allowed to use up to 10,000 steps. Each simulation may need different number of steps to complete. One may reach a win or dead state in just 10 steps, and another may get there after 1,000 steps. We also set the number of steps for epsilon, greedy, and nil to be 30,000, and after that a random move will be chosen only 10% of the times to allow for new moves to be tested and explored outside what it has learned. After a while, you'll see that rewards are increasing and you start getting 0.6 rewards, which is the maximum possible reward. Even if you learn a perfect policy, the learning agent still keeps exploring 10% of the time, which is why you won't always see perfect 0.6 scores near the end. Some of the outputs that you can see in the printed log are current step number, reward received at the end of an epoch, current epoch number, which basically is the current simulation count, and you can also see the current value of epsilon, which sets the exploration percentage at any stage of the training. You should also know that due to inherent randomness of both the model and training setup, running the same training multiple times may result in policies that perform slightly different. Therefore, you may need to repeat the training or change some of the hyperparameters to improve the policy's performance. To get access to the learned policy that is saved in the Statechart underline policy.zip, we need to get to our projects folder. To do so, right-click on the AL webinar, which is the project's name, and select Show in Explorer. Then go inside the AL webinar folder to see the Statechart underline policy.zip. Copy the zip file, open the AnyLogic model folder, and paste it here. Next is to make some changes in our original AnyLogic model that we used as an environment for enforcement learning. This time, we want to use the simulation model as a test bed to evaluate the performance of the learned policy. First, we need to add RL4J as a dependency to the AnyLogic model. To do so, click on the model name under Projects view, and then in the Dependencies section of the Properties window, select and add RL4J. This is the same library that we added to IntelliJ for training, and we'll now use it again to allow our model to use the trained neural network. Next is to add some code to the main agent. Click on main, go to its properties window, and find the advanced Java section. I copy-paste some code to import some of the needed libraries, mostly from RL4J. I also added some code to the additional class code section. Here we'll load the learned policy into AnyLogic model. I declared a DQ and policy variable here. I also added a string variable with the value as our zip file's name. And here I loaded the policy knowing that the zip file is already copied into the AnyLogic model folder. There is a try catch statement in case there is no policy with the provided name found in the model folder. To execute the policy, we need to add an event from the agent palette. Set its mode to cyclic and so that it happens every second. I copy-pasted the needed code in the action field of the event. Here the code says that if the use policy parameter is set to true and we have a policy that was imported to the model, then read the current state of the model by calling the getObservation function, get the learned action from the saved policy, and pass it to the takeAction function to execute the selected action. Now that the trained policy is ready, we can run the simulation with the policy and observe its performance. Click on the simulation experiment and in its properties window, click the use policy checkbox, which means that the value of the parameter is now set to true. Now we can run the simulation and see it run with the policy. As you can see, the learned policy is now in control and automatically controls the AGV to the win state and to get the highest score of 0.6. I can run the model again and it was able to move the AGV to the win state but with a suboptimal score of 0.5. As you can see here, the learning agent has learned the correct tactic, which is to recharge the battery whenever it slips and start over again with a full battery. If you want to run hundreds of simulations and get some statistical performance measure like the average score, we can automate the process by running experiments. For example, here we can either use a first-order Monte Carlo or parameter variation experiment with replications. I chose parameter variation since it is included with the AnyLogic Personal Learning Edition. To do that, you need to right-click on the model, select New, and then Experiment. Select the parameter variation experiment and press the Finish button. Under the Parameters section of the Experiment's Properties window, change the Use Policy value from false to true. Slip chance should be 30%. We also need to select random seed for our simulations, and the model stop time should be set to 10,000, which is equivalent of 10,000 steps set during the training setup. Under the Replication section, check the Use Replications and set the replications per iteration to 100. To be able to record and show the results, we are going to use a histogram. Go to Analysis palette and drag and drop a histogram object to the Parameter Variation Experiments canvas. Now go back to the Experiment's Properties window and find the Java Actions section. On After Simulation Run field, type data.add root.score. We basically add the score from root, that is a top-level agent, to the histogram object. You can see here that the top-level agent is set to be main. After each simulation run, the value of the score object will be added to the histogram data, and this will be repeated for 100 simulation runs. To be able to see the histogram, right-click on the data and select Create Chart. To show the average score, check the Show Mean, and you can modify some of the visual settings if you want. Now you can right-click on the experiment, run it, and observe the average score over a sample of 100 runs. As you can see, the average score value is around 0.58, which is very close to the ideal of 0.6. Since this model is relatively simple, by tweaking the hyperparameters of the training setup, the agent should be able to learn a perfect policy that results in a score of 0.6 in all scenarios. As mentioned, due to the random nature of the training process, policies from your own training may be different from what you see here. For your reference, we will provide a learned policy in the supplemental material. The reinforcement learning setup and the hyperparameters are intentionally not tweaked to perfection so that you can experiment with it and find better or more efficient setups.
Okay, thank you for your attention throughout the webinar. There are some questions here that my colleague Tyler Wolf Adam helped me to put together, and it's a summary of some of your questions. But before I go through those questions, I wanted to reiterate some points about the webinar. As you remember, I mentioned it during the webinar, we used an exported model for the training, and that is not possible with AnyLogic PLE or Personal Learning Edition, the free version. You need to have professional license, and because of that, we are going to provide that exported model in case you wanted to try it and replicate this training environment. Okay, so let's go through some of these questions, and then I will go through the last things to clear. Okay, first is it's a kind of broad question about what are the most important hyperparameters that you use in the training. I'm trying to show you some of those. This is the IntelliJ, and I'm showing. So as you can see, some of the hyperparameters that are very important are definitely the number of hidden layers on your network, number of nodes for each layer is definitely going to affect how the neural network is capability to learn something from the training, and also the max step, the maximum number of steps that could be tried in the total number of simulation. And max epoch step is also very important. It gives you more room in each iteration or each epoch or simulation to actually try and and learn from that run instead of interrupting it in the middle. And one other important thing would be the epsilon. And this epsilon, the minimum epsilon, sets the minimum value for exploration. So here we have the epsilon greedy annual step to be 30,000, meaning that after 30,000 steps out of 100,000 that we have, so it starts to use the policy that it learned so far, and like in the rest of 70,000 steps, 10% of the time it's going to explore a new action and try to learn something new. So these are some of the important hyperparameters that I can mention, but there are many others that you can just look into and read from the documentation of the RL4J, and also from the like the written explanation of this code that we sent to you with the follow-up email. Okay, why you model the movements by state charts? That's a good question. There are different ways to model something like this. We intentionally chosen a state chart because I think, I personally think state chart has lots of potential to be used for reinforcement learning, specifically because the states are in this type of modeling is very clear, and there is it's very easy to observe the current state of the model and make decision based on it. So here, for example, when the model looks at the state chart, you clearly in one of those states, so you can clearly see where you are. Compare it to other models, for example, the traffic light model that we showed in AnyLogic conference. There are tons of cars there. There are many bits of information dispersed in that model, or in even like a process-centric model, the state of the model is distributed over all the blocks. Here you have this kind of atomic like state, and you can clearly see where you are. And a state chart is a very powerful construct, can be used for modeling like sentient kind of behaviors, robots, machines, and it's a very powerful, very clear and visual way of building models. So that's why we selected it for this webinar. Should there be any intermediate reward for getting closer to the destination? Could you change the reward to make it less sparse? Yes. So you should know that a definition of the reward, or like this, the reward scheme that you set up is an art. It's just like even like in a real life, if you wanted to like set some incentive for human to do something specific, it's just a really hard thing to design, and even like social policies always have challenges to do that, because there are ways to exploit that reward scheme, and you might end up in doing something that was not desirable. So here definitely we could have tested other scenarios, like trying to give it some guideline that if you are moving in this direction, you are moving toward a better like solution. But we decided to just have one reward at the end, and it actually another objective that we had here for designing it like this was to see if it can learn on its own without any help or nudge toward the best solution, and it actually did. So that is interesting. What was included in the observation space? Couldn't we just use one number to represent the current state? So if you look into the observation state just tells you which state you are, and also it tells you the ratio between the current power level and the full or like the power capacity. So these two information tells you where you are in the state chart and also your battery level. And based on that, it makes a decision. To make it work better with like reinforcement learning and deep learning part, we use a one hot array, and the reason for that is when you are using a one hot, it's basically an array that says one. For example, if you're in state one, you will have a one for state one and zero for the other states. And because of that, it works like an indicator variable, and it communicates very clearly that we are not dealing with a numerical value or an ordinal value, and it helps a lot in the learning mechanism or like process. And the last one, can we do the training from inside AnyLogic? Yes, you can do that. And if you're interested to do this, you can look into our traffic light example. I did a presentation in AnyLogic conference, and we also had a weblog, a blog about that. And in that blog, you can see how we do the entire reinforcement learning training inside a custom experiment. Here we had an empty experiment, and we did everything inside IntelliJ with an exported model. In that setup, we put all these code inside the custom experiment and did it from inside AnyLogic. We wanted to show this option because eventually you will be able to do the same thing by connection to AnyLogic Cloud. You don't even need to physically import all the jar files into this environment. With just some API call, you connect with the AnyLogic Cloud, and you can do the training in any IDE. And we are working on different ways to do that, and the Python API is also is coming very soon. And when those things are ready, we definitely have another webinar to showcasing how we can do that with AnyLogic. Okay, so I guess that's all the questions that I had for today. Our time is up for today, and again, thank you so much for attending this webinar. We are trying to have more of these kind of webinars in the future. Don't forget that your feedback is very important for us. You will get a follow-up email after this webinar, and in that we will send you all the material you needed to replicate this model. The AnyLogic model, the exported model, RL4J library, and everything else that you need, and also some documents that explains the code in more detail. Thank you again, and have a great rest of your week.